Whose job was that? Whose job was to hit record?
I'm sorry.
All right, I'm recording now. Here is this problem. So we're looking for the sixth derivative of this. This represents a polynomial, an infinite polynomial. So we're going to be taking the derivative of a polynomial. To find what this polynomial looks like, I'm just going to run out a few values of k, and we started at 1. So my first term is going to be -1 x squared over 2. Now when k is 2, this squares the negative number, so it becomes a positive 1. And I get x to the 4th over 4. Now k is 3, -1 to the 3 is a negative. This gives me x to the 6th over 6. The next one then will be positive x to the 8th over 8. So you can see it's all even powers alternating. We're looking for 6 derivatives of this. So let's just start knocking out derivatives. The first derivative of this thing, just using those terms, will give me -2x over 2 plus 4x cubed over 4 minus 6x to the 5th over 6 plus 8x to the 7th over 8 minus 10x to the 9th over 10 and so on. So you can see that those constants will cancel and our first derivative just looks like this. He's got odd powers on the x's. Now my second derivative will give me -1 plus 3x squared minus 5x to the 4th plus 7x to the 6th minus 9x to the 8th and higher powers. We having fun yet? Here's my third derivative.
I really hope you're gonna have a lot of fun.
That's what we're here for. We're here for a good time.
There is a cube. There's a cube on that one.
I got a cubed here. There's 3. And my fourth one gives me 6 minus 60x squared plus 5 times 42. I give up right there. X to the 4th minus 72 times 7. I'm glad I gave up a step earlier. All right, I've got, which one did I want? I want the 6 derivatives, 2 more. I'm getting excited here. There's the 5th derivative. Oops, big parentheses. That is 0. I get 120x plus 4 times 5 times 72, which would be 6 times 7, but I'll just go ahead and write 42. X cubed minus 72 times 7 times 6, and x to the 5th, and more terms. Here's my 6th derivative. As a function of x, it's going to be minus 120x plus 3 times 4 times 5 times 42 times x squared minus 72 times 7 times 6 times 5 x to the 4th plus higher power terms. And not only did I want the 6th derivative, oh, I took a derivative here. I wanted the 6th derivative evaluated at x is 0. So at x is 0, what term is left? Because everything from the second term on out has an x equal to 0 in it. When I substitute to get this. So all of those terms will vanish when I substitute 0 in for x, and only one term is left.
-5.
And that's the -120.
We got lazy and
We got lazy.
we took a bunch of derivatives in our head
And
and
then
we got -5 factorial.
it
Because
would work. I gave you that, didn't I?
yes,
Because we recognized the pattern that we would have gotten the factorial of the derivative divided by whatever this looks like after I've taken power down, raised it to 1 power less.
Just the term with the 6 in it.
Yeah, so it's just the value of that thing there, the coefficient. But I chose it small enough that you could have done it out by brute force. Anybody else want in? All right, what about bonus? Who recognized the bonus? What was this? What was this thing here? What does this look like? Does anybody remember the power series for that one?
1, right? Plus x.
1 plus x
squared
plus
over
x squared plus x cubed. So if we wrote it out, that was what, x to the k? Oh, I got factorials. So it looks like x to the k divided by k factorial from k is 0 to infinity. So what does it look like when you put a 2/3 in for x? It looks like 2/3 to the k divided by k factorial, which is the same thing as saying 2 to the k over 3 to the k times k factorial. So that's the first part of the bonus. It's to recognize this backwards came from that. So that power series converges to e to the 2/3. The second one was a little bit harder. You had to remember the inverse tangent. I've forgotten the inverse tangent.
Sign without the factorial.
Sign without the factorials?
Yes.
So it looks like x
X
minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, x to the 9th over 9. And so if I replace x by the square root of 2, we have the second problem in the bonus. So this was just, see if you memorize these things, I guess.
Yeah, literally like 5 seconds before the test, I was like, what's wrong with that factorials?
So that's what I wanted for the second one. That shouldn't have nearly been worth as many points as I gave you. But I probably have 4 glasses of wine and points. Everybody gets points. Now I graded in the morning, so I didn't have too many. I just had just enough. I graded all weekend long. What a wasted weekend, and I still have more. So instead of having class today, we're going to go grade my trig tests.
Okay, that's so great.
I can't. That's a FERPA violation.
So who? FERPA?
Private information about my students.
What does FERPA stand for?
I don't know. I just know that it's.
F, what could the F stand for?
Man, I don't know.
Federal.
Fun, federal, good.
We'll look it up.
E,
Education.
education, regulations,
Privacy.
privacy, act.
Probably
I think we did it. I think we did it.
This is different.
Federal Family Educational Rights and Privacy.
Oh,
A little bit
family,
off.
family, we got that federal out of there.
A little bit off.
That, we did good, we did
It
good.
wasn't federal law, so makes
It's a
sense.
law, it's a law. I could go to jail if you
Enacted
graded
in
my.
1974 that protects the privacy of student education
Are you
rights.
going to jail for that?
No.
Oh, I was like, what? That does not seem that serious.
They
No,
probably
but
like,
hey,
We-
man.
We are all hired graders.
Okay, so everybody knows the statement of the limit comparison test. If the limit of AK over BK is positive and finite, both AK and BK do the same thing. Can you state me the zero infinity cases? What if the limit is 0?
Converges.
You guys chant so well at the ball games when you're chanting obscenities. You don't want to hear these words. But when I ask you to state something in class, it goes.
I keep my mouth shut even if I sit in the violent section.
Oh, no, I was
I
in the
don't
most
do
violent section.
I'm down
I
there
know
with
you yell.
the former regent's 5 grandchildren. And there's,
I played rock, paper, scissors with number 57, okay? That was so much fun. I beat him,
7.
yeah, on Oklahoma State.
I told 42 and used to fire his barber. He didn't like that very much.
We asked number 89 what his GPA was. He didn't like that one.
Oh, is that why you started
Anyway,
flipping us
the
off?
zero infinity case says that if you take the ratio of the AKs with the BKs, your lookalike die, and you get a limit of 0, then you can claim that AK converges if and only if the BKs converge. The opposite is true if the limit is infinity. If you take that limit and get infinity, and you know that your comparison series BK diverges, then the series that you're testing, AK, will also diverge. And so that was the statement on problem number 7. The BK sitting down there underneath the AK is a 1 over K. And everybody and his dog knows that that diverges. And if your dog doesn't know that, quit teaching him how to sit and teach him about divergent P series. 1 over K, my comparison series diverges. The ratio of the BK to the AK is infinite, so that is the statement of the infinity case. AK is also going to diverge. So some of you will tell me that the AK would have to grow faster than the denominator, and the denominator has a limit of 0, but that wouldn't be true if I had simply replaced that with 1 over K squared. If I had a 1 over K squared down there and got a limit of infinity, I don't have a conclusion. The fact that I have a divergent P series under there in my limit is infinite, then I can make the conclusion. Okay? All right, what else?
Jack says he wants you to move the camera to the left.
There's what Jack thinks.
All the way to the left? Let's see if I remember how to do this.
Usually it's just right there, but no.
Don't we have 2 Jacks?
No, we have a Jack and a Jackson.
Oh,
Yeah, it confused me at first too.
Jacks.
There it is.
I
There's
mean,
the
you're learning
bonus.
this a little late, Eugene.
There's the bonus.
It's the end of their semester. We're trying.
Okay, so the next
Are you going for finals?
act of business is our next test occurs on the Friday that we come back from Thanksgiving, is that correct? Which is December
3rd.
3rd.
Yes.
It's at 10:30 in the morning and it is not in this classroom. Number down.
We're talking about class on December 3rd.
Final exam, Friday, December 3rd.
You know what, I'm gonna put this down somewhere where I'm not.
Change out what the thing is called.
I'm gonna go to
We're
the
gonna
wrong
get
place.
lost.
I'm gonna go to the wrong place. But I got lost the first time I went to my calculus or my chemistry exam. I got lost. I ended up finding the like full panic attack.
For physics, we just have to like remember to not go to the classroom and to take it.
10:30 until 1 o'clock. It is still in this building, 1 floor up.
So I just-
I think math 108 is the very first classroom you encounter on the first floor. If you enter the building, go up that little small flight of stairs, I think that's the one on the corner.
10:30 to 1. Yeah, it's like the same amount of time it took for the last test.
Is this your first final? That-
Yeah.
Everybody does well in their first final. It's like your 3rd or 4th one that you really studied.
I think this is my
It's your 3rd one. 3rd is right there on the line where you start this now.
First part was.
And so I want you to do well because I don't take corrections on the final. You get what you get when you do it. And that's why I tried to pad your score quite a bit in these last few exams with your bonuses. It won't be a hard final. I'm not trying to scare you, but I don't write it, so.
One of the write-ups too. I still have one.
You still have a lot? You know what's more fun than going into finals?
That's not
Going into finals with a boatload of grading to do. Let's say everything is due on the last class day, because I'm not allowed to make anything due on the study. Last class day is Wednesday, the 1st. All write-ups due Wednesday, the 1st.
I've got 3 chapters to cover.
Yay! You can send them to me a little at a time, and that way I won't be overwhelmed.
No, just send her all of them in separate PDF documents. One page, one problem per. All right.
The time, like, time email, so it goes off at the same time, every single one.
Or maybe you just won't have to do any write-ups if you can get that blower out of that guy's hand.
All right, challenge, hey, challenge accepted.
Finish your class, let's go.
No, I'm serious. She's serious.
I'm not serious. I can be loud, I just don't particularly like it.
I really wanted to like look through that window and watch him talk.
All right,
We could all just
we've
stare at
got
it.
one more chapter left, but actually only 4 sections of chapter 9. Many of you have already had your physics 1. How many of you have completed physics 1?
I mean, well, we're about to finish
And
it.
so in physics, you were introduced to vectors and their applications.
Ooh.
What kind of vector operations have you done in physics?
And cross.
Dot and cross. So there's not a dang thing that I'm gonna do new for you.
They actually taught y'all what those were.
Yeah, well.
Our
kind
physics
of.
professor was just like, just.
Yeah, so I'm very
Yeah,
excited.
well, maybe I'll show you some easier ways to do things.
Well, I wasn't like.
So, in chapter 9,
Oh, really? I'll use the-
Chapter 9, we're gonna talk in the first two sections, vectors in 2 dimensions and vectors in 3
Can I talk
dimensions.
about this?
I know, I never knew how to do that.
Right.
What is gang?
Right. We did it in terms of like, physics, so you had a velocity. And you had your- No, you had your
All I remember is
velocity.
VBF.
I don't know what they are.
There's one that was FBI.
Actually, in physics, we don't learn that.
My
We
big
instead
mistake was I
learn the
always
color.
field to the right.
Yeah. So pretty much like if you have like if you have like a current going through a wire, like there's several different versions. Like if you have a current going through a wire, then you can throw your wires around it, and that's the way the magnetic field.
I remember you
Actually,
shooting
in
electrons
physics, we
into a
learn
magnetic
the
field.
Car brand is
shows
the
the
one
way
that's
that-
like
Yeah, yeah, so this is velocity. This has to be.
That's what I just
your
said.
electric field.
That's what I just said.
I don't remember. I just remember writing.
Whatever direction it rotates.
Okay, come back to me. There are 2 sections here. We're gonna talk about vectors in R2 and vectors in R3.
Wow.
R2 is a fancy way of saying the XY plane. So in R3, we're in 3 dimensions. In 3 dimensions, we've got 3 coordinate axes, X, Y, and Z. And typically we draw them like this, in that the Z axis is here, the Y axis is here, and then the X axis is coming out at you. So it's coming out of the board straight at you, the positive X axis. Positive Y axis goes to my right, the negative Y axis goes to the left, positive Z that way, negative Z this way. So it takes 3-dimensional space and cuts it up into 8 octants. We got 4 quadrants here. Draw those as planes, and you can see you got 8 octants. So I can't draw the 3-dimensional look very well, but this is going to be the X-axis coming at you and going back in the board.
I've never seen that notation before for dimensions.
Well, now you have. That's why I wrote it that way. I wrote it that way. But now you've seen it. R is the set of real numbers. So if you just see this,
Oh.
here's the picture of R. Right, that's the group photo, all real numbers. This is the set of all ordered pairs, and this is the set of all ordered triples of the form X, Y, Z.
So what would the fourth one look like?
Well, in math, we have n dimensions, right? You can't draw n dimensions, but you have n components. Say x1 out to xn would be your n tuple, right? That's how you would label your points location. If you want 4th dimension, you can think of your 4th dimension as being time. So your position in space and the time that the object is at that position. But if you generalize it to n, that's just for fun in math and physics. We look for fun in every weird way we can.
Does it matter which one you put as X, Y, and Z on the triples?
Our book will use this picture and it'll denote a particular point in space, X first, Y second, Z third. For instance, if I want to plot the point 1, 3, 5, I go out at you 1 unit. So I'm going to go 1 unit in this direction. And then standing from there, I'm going to head that way 3 units. So I'm out of the board here 1 unit. And then I'm going to go 3 units that way. So from here, 1, 2, 3. And then I'm going to go up 5. 1, 2, 3, 4, 5. So it looks like it's 2-dimensional, but it's not. Go out 1, 3 this way. Watch the up 5. If I want to plot a negative number, if I need to go back in the X direction, say I want to go back 2, left 5, down some, then I would put negative coordinates.
I have a question.
Yes, sir.
With these 3-dimensional coordinates, We could still find a two-dimensional slope, right?
Kind of. If you look at a line in the XY plane, so let's take the line that goes through x is -1, y is 1. What's the equation of this line right here?
Y
Y is equal to x plus 1. So let me draw it for you in this plane. It goes through x is -1 and y is +1. So it's back there in the board. So my XY plane is a little tabletop. And that line holds for all values of z. And so what we get in 3 dimensions is that this equation in 3 dimensions is a plane. In 2 dimensions, it's a line. In 3 dimensions, it's a plane. Right? The y is equal to 0 is typically the x-axis. Y is equal to 0 is a plane that is parallel or perpendicular to the x and to the y and z axes. So look at a parabola. Draw the parabola, y is equal to x squared in 2 dimensions. So now let's do it in 3 dimensions. So here's x, and we're going to open up about the y-axis. So let's do it right here. There's the x-axis. So I got a parabola that opens up about the y-axis. It's going back there in the board. That becomes a surface. Something like that. And it's going to extend infinitely in that direction, infinitely that way, and that way. And even though it's not closed, that surface in 3 dimensions is called a cylinder, taking the shape of y is equal to x squared. So it looks like just a bended sheet opening up perpendicular to the XY plane. So take the equation of a circle. X squared plus y squared is 1 is a circle centered at the origin of radius 1. What does it look like in 3 dimensions? It's a cylinder symmetric to the z-axis. What about in 3 dimensions? What do you think the graph of y squared plus z squared is equal to 1? Circle symmetric about the x-axis, right? So y squared plus z squared will be the circle coming out at you and going back in there. Okay. Okay, so that's what things look like in 3 dimensions. So let's talk about a vector in 2 dimensions. A vector is an object that has a direction, tells you which way it's going, and a magnitude. If you watch the weather forecast, and when the forecast calls for wind, they draw a bunch of arrows on the state of Texas map. Some of them are little, they get little bits of wind, and some of the arrows are big. That'd be Lubbock, getting the big bits of wind. And it tells you the direction from which the wind will be coming by drawing the arrow with a head on it. That's an example of a vector. It shows a direction with a certain magnitude, a size. A vector is any entity with magnitude and direction. Magnitude stands for size. So in 2 dimensions, in the XY plane, plot the points 1, 4, and Q -2, 1. Plot those points in the XY plane. X is 1, Y is 4, there's point P. X is -2, Y is 1, there's point Q. I can draw the vector from point P to point Q to be just an arrow with its tail at point P and its head at point Q. So the vector from P to Q would be denoted like this, with the arrow in the direction that the vector is moving. So that would be something different than the vector from Q to P. The vector from Q to P would have the arrow at the terminal point P. We describe the vector by components. How far it's moving in the X direction will be the first component. How far it moves in the Y direction will be the second component. There's not that many leaves out there. And why are they doing that today? Right? Nobody's gonna be here on campus all week.
Because it makes the most sense to do it when at least some people are here. They have to annoy someone.
Yeah,
They have to let everybody know that they're doing things.
they gotta get paid for
If
something.
no one's
right?
here to listen to them do their work, did they really ever do the work?
What is the tree really?
The leaves could have just got up and left on their own.
Okay, so the components of vector PQ, to make you read it as a vector, we put the parentheses for a point, and we use these sharp brackets for the vector. And so we look at how far this vector moves in the X direction, and it went from X is equal to 1 back to X is equal to -2. So this total length here is a grand total of 3 to the left. Right? And so I use as my first component the description that we go 3 units to the left. And then I went actually 3 units down as well. This is the Y coordinate 4, and my terminal point has a Y coordinate of 1. And so I went 3 units down. That's unfortunate. So this is the distance that I went to the left, and that's the distance that I went down. So that's how I can describe the action of the vector from point P, wherever point P is, and then down. Then I can describe its magnitude based upon the Pythagorean theorem. Magnitude is how long that arrow is. And it's the hypotenuse of that right triangle whose legs have these lengths. So I can figure out the magnitude of PQ. Put it in absolute value bars. Some books will use double bars. Let me see what your book uses. I think your book just uses single bars. Nope, it uses double bars. So those double bars would be the magnitude. It's just going to be the Pythagorean theorem. You take the X direction and it'll be a direction, so you really don't need the sign. You take the X term and square it, and the Y term and square it, and that'll be the square of the hypotenuse. And so we take the square root of it. So this particular vector 9 and 9 is 18, has a magnitude of the square root of 18, or 3 square root of 2. Magnitude is a positive number. It describes a length. The components of the vector would always have the X coordinate direction here, and its initial X from point P minus, nope, I said the other way. It's terminal minus initial. Terminal point minus the initial point. Why does my 1 look like that? Terminal point minus initial. So I'm going from Q to P. So this one would be 1 minus 4. So you take the coordinates of the terminal point minus the coordinates of the initial point, to get the components of the vector. So in general, if I'm going from point P, whose coordinates are x1, y1, to point Q, x2, y2, from PQ gives me the vector PQ with components x2 minus x1, comma, y2 minus y1, in the x direction and in the y direction. And then just for the sake of argument, we're going to call those points A and B so that I could write you the magnitude of PQ as being the A squared plus the B squared to give me C squared, but I want C. What was that little beep about? The same will be true in 3 dimensions, except for we'll have a third component. If I'm in 3 dimensions, I'm going from x1, y1, z1 to x2, y2, z2, and I'd have a third slot in here, which would be z2 minus z1. Magnitude will be done the same way. We would add to this the value of that third component squared and put it under the square root sign. So in R3, from point P, x1, y1, z1, to point Q, x2, y2, z2, gives us vector PQ, whose components are as before. But then you have this third feller. And so if I just call those simplified versions A, B, and C, the magnitude of vector PQ is the sum of the squares of the components under the square root sign. So we run out of alphabet when we do this in n dimensions, and we just use subscripted x's and y's or subscripted a's and b's. So in n dimensions, you can represent a point as having coordinates a1 out to an, the next point having coordinates b1 out to bn, and then you subtract to get the components of the vector and the sum of the squares of all of the n terms under the square root sign. So there's nothing magical about being in 3 dimensions. Every vector in the xy plane is associated with a position vector. And that's a vector that has the same direction and the same magnitude, but its initial point is always the origin. The position vector associated with this vector PQ is found by plotting the point -3, -3, and connecting that to the origin. So if I did that red, if I go over here and go back 3, down 3 in the XY plane, but now draw this vector, red, here. I'll make this point bigger. I'm trying to make it. It should be a vector that has the exact same length as that one and the same direction, so it would be parallel. So a position vector associated with vector PQ has its initial point at the origin and its terminal point corresponding to these directions. And let's just call that vector V. Position vector always has its little rumpus on the origin and arrow at the coordinates of that point. So vector V is called a position vector associated with vector PQ. And we do that so that when we're in higher dimensions, we don't have to worry about plotting points with a bunch of components. We just figure out the A, B, and C that I'm considering the components of the vector, and then we'll graph it from the origin. So other than maybe my example of the wind map on the weather, give me some other examples where a vector has a physical interpretation. What do vectors do in physics?
They demonstrate forces.
They demonstrate forces acting on an object. A force has a magnitude and a direction. If you want to push something that way, we've got one direction with a certain force, push something that way. So a force is an example of a vector.
Velocity. Acceleration.
That's right. Force,
Jerk, snap,
Velocity.
crackle, pop.
acceleration,
Fields. Yeah.
any kind of field, right? When you're talking in electrical engineering, you have these magnetic fields and things like that, right? Things that have a flow to them, right? You've got
Fluid dynamics.
fluid dynamics, so anything that describes a motion and a direction.
This too. Electrical field and electron cloud.
That's right, any kind of field whatsoever. When you get in differential equations, you're going to draw things called slope fields. So you're going to have a formula for a derivative, and you're just going to plot a lot of the derivatives. And the derivative depends on the point. So sometimes the derivative is steep, so it'll be longer and in a different direction, and sometimes it's not. So in a slope field, we're describing the derivatives of a particular function, anything that has a rate of change. You may have seen another way to write vectors, and I'll get to that, but first I have to describe some of the operations that we have. When we talk about vectors in the XY plane or in 3 dimensions, and we want to do things with them that involve just an actual number or describe a number instead of a vector, then we call that number a scalar. A scalar is just your regular old number. So here's the number 0. Here's the vector 0. What do you think I mean by the vector 0?
Not going any that way.
It doesn't have any magnitude or direction. It's kind of like we're going to make an algebraic ring out of vectors. So it has to have operations that are commutative, associative, distributive. It has to have an additive inverse and some version of a multiplication type thing. This 0 vector is going to be the additive inverse of vectors. It's a vector in 2 dimensions whose components are all 0 and whose magnitude is 0. So it's the vector that has no direction and no magnitude. If you draw its position vector, it just looks like the origin. When I take a vector and multiply it by a scalar, if I take, say, the vector A, B, and multiply it by some scalar K, that operation is done component-wise. So if I take the vector, say, 1, 3 as a position vector and multiply it by 5, I get the vector 5, 15. Let me draw those as position vectors in the XY plane. Oh, I think such a big number. Make it bigger. Okay, so let's say that these are in clumps of 5. All right, so 1, 3 would look like something like this. There's that vector. The position vector associated with that. So let's call that vector V. There's vector V. And now let me plot the vector 5, 15. Each of these were 5. So there's the vector whose terminal point is at the ordered pair 5, 15. And I'm going to draw it in blue. And it's going to look like, well, I'm going to just move it over a bit. My scale is bad. Because it should be a vector that is in the same direction. And all it should look like is 5 of these guys laying end to end. 1, 2, 3, 4, 5. There are 5 these laying end to end. It should be a vector exactly 5 times as long as that vector. If I figure out the magnitude of vector 1, 3, let me write it like this. And you might see it like this. And we put the 2 little bars around something that's asking you to find the sum of the squares of the components and then take the square root of it. So in our example, you get the square root of 10. So let's compare it to the magnitude of this one. Magnitude of 5, 15 would be 5 squared plus 15 squared under here. So that's 25 plus 225 or 250, which is 25 times 10. And the square root of 25 is 5. So it is a vector exactly 5 times as long. So scalar multiplication of a vector produces a parallel vector in the same direction whose magnitude is k times larger than the original vector. Okay. Keeps it going in the same direction, but k times larger. If k is a negative number, then it goes in the opposite direction. If I take this vector and multiply it by -2, -2 times the vector 1, 3 goes back 2 units and down 6 units. So if I go back 2 and down 6, it's just going to look like this. It's going to have twice the magnitude right here. So -2, -6. It's -2 times vector v in the opposite direction. But it has twice the magnitude. Minus sign just gives it the direction. Yes, sir.
So technically, if that, so the only reason that a scalar can only affect the magnitude of a vector is because a scalar is only a value with a magnitude. It does not have a direction.
And because it changes the size of each component.
Yes.
So that means it's going to change the magnitude of
So
that exact number.
wouldn't -2 be a vector?
No, -2 represents the scalar.
I thought negative and positive represented direction.
If we associate them with some size, with a vector, telling me direction from where. So it's got to be applied to a vector. The number by itself means nothing. But when you multiply it with a vector, now it does. Now it changes its direction, heads it in the other way. So the scalar multiplication is something I needed because sometimes we describe vectors in terms of standard basis elements in each space. In R2, every single ordered pair can be some linear combination of the ordered pair at 1, 0 and the ordered pair at 0, 1. And when I use those as the terminal point of vectors, then I'm describing the standard basis vectors in R2 in terms of, let me draw them. I don't know. Here is R2 again. Here's the ordered pair 1, 0, and here's the ordered pair 0, 1. And if I use those as the terminal point of vectors in standard position, this vector, the vector 1, 0, is denoted as the standard basis vector I. Sometimes you'll see it with an arrow. I like to put the little hat on it like that because math is fun because you can put hats on letters. It's like dogs are fun because you can put bandanas on them. This is the math version of the bandana. So that's the standard basis vector in the X direction. The standard basis vector in the Y direction will be denoted J. And every vector in the XY plane can be written as a scalar multiple of those. For example, the vector 1, 3 looks like 1 times I plus 3 times J. So I got to tell you what it means to add vectors. To add two vectors, you do what you think you should. You add them component-wise. Vector addition or subtraction is done component-wise. For example, if I have A1, B1 as the components of one vector, and I add to it A2, B2, you get what you think you should get. A1 plus B1, A1 plus A2, comma, B1 plus B2 as the components. So that's what I mean here. I would just add one of these with 3 of those to get that one. In 3 dimensions, if this is the z-axis, then the standard basis element in 3 dimensions would be the I, J, and K vector. So in R3, the standard basis vectors are I, which looks like the vector that has a 1 in the first slot, zeros elsewhere. The vector J has the 1 in the middle slot, zeros elsewhere. And the vector K has the 1 in the third slot, zeros elsewhere. And the idea is every vector in 3 dimensions is a linear combination of those 3. When you get to linear algebra and talk about a basis, the basis is the building block, the skeleton that you can use to make all other things there. Or to speak linear algebra, a basis is something that is linearly independent and spanning. You'll hear that again in a few semesters.
We can drop out.
You can drop out. Practice. Would you like fries with that? Here's your future. You get to wear this cute little uniform to work every day and a hat.
That's the selling.
The bandana.
The bandana.
No, why would I put a hat on letters like I put a hat on myself?
Exactly. You can't wear it backwards.
Teachers.
And
No, you can't, because you can't wear it backwards. Your hat has to be that way. Backwards hat guy.
Get
I
fired
think my work here
fast.
is
Okay, I
done.
want to
See you
show you the
later.
geometry of addition. So let's draw two vectors in R2 and let's add them and see where their sum is.
Turn his head around.
Vectors describe physical entities, so you can actually see what scalar products look like and what sums look like. Let's see if I get pretty numbers, so I don't have to.
My physics teacher he was kind of almost. He went to Angelo State University.
Just get
He's not of that.
I sincerely hope.
Sometimes I'm like,
But he said he could sing, and he can. And so they let him do it. And he has he showed us a picture of him in the black 50 choir at ASU. And it was like the funniest thing I've ever seen in my life. But he gave us like we had to like pretty much calculate all the numbers for defense. That was our first problem that we ever got. So we worked like 3 weeks because he just kept on putting and adding stuff.
Okay, let's go ahead and draw these two as position vectors. And then we'll add them and draw that as a position vector. Let's make the scale kind of large. I'll try to make it equally spaced. So that'll be 1 unit. All the way over 6 units.
You actually have to go over 9.
And I'll have to go 6. So I hope I space them equally. So the position vector associated with 1, 3 is over 1, up 3. That one. Then the position vector associated with 4, 6, over 4 and up 6. Is here. All right, now let's add those two, the way we said we would component-wise. 4 plus 1 will give me 5. 6 plus 3 is 9. And so let's plot that and draw that position vector. Let me draw it in blue. Over 5, up 9. Oh, and it runs right into my little thingy here. Get my hand nice and steady here. Oh, it's wiggly.
You shouldn't have even said that. It's like,
I know.
it's like saying a guy's kicking percentage before he kicks a field goal.
Okay, okay. So that's really crooked. Let's try it real hard. Oh, and I missed.
Just move your dot.
With my dot. We call it the big dot principle. You just make it bigger until it goes through it.
Precision erasing.
Try this way. Sounds like I'm killing the marker, doesn't it? Okay, so what I'm trying to show you is that the sum of two vectors yields a vector and not just any vector. If I pick this one up, it fits right here in the same direction and the same length. So there. And if I pick this one up, it fits right there. But I picked a horrible example to show you that the sum of two vectors is actually the diagonal of the parallelogram whose sides are the two vectors. Sum of two vectors is the diagonal of the parallelogram whose sides are the two vectors. So I should have done my example at 6:4. That way it could have been a little bit wider and you could have seen it. would look like this. They're both position vectors. Like that. So this is vector V and this is vector W. And if we make the parallelogram, copy that vector. It's about that long, copy that one. And V plus W, right, is that one.
But they had to be going the same direction.
What do you mean?
Like how on that one, they're both going at this angle.
Uh-huh.
On our V and W, they're going two different angles.
The angle didn't matter.
Okay.
Just make the parallelogram. Now, so subtraction would be kind of the same, because if I want to find vector V minus W, well, here is vector, let me draw them over here.
It's just
I
like
have
adding the
vector
opposite
V.
of W.
Here. And vector W there. Then vector minus W goes this way. Right? And so V minus W is the same as V plus minus W. Would be here. That's the vector V plus minus W. That vector would fit right here. The vector V minus W can be interpreted as the vector whose initial point is here at the terminal point of the vector being subtracted, and whose terminal point goes back to vector V. And V minus W is found by adding V plus minus W. Treat the minus sign as scalar multiplication by -1, and then go component wise. So for example, if I want to subtract these two vectors, 1, 3, minus 4, 6, I just subtract component wise. 1 minus 4 and 3 minus 6.
Oh, hey, look. One from the beginning of class.
It is. Reared its little ugly head again. Okay, so we have scalar multiplication and vector addition and subtraction. Addition represents the diagonal of the parallelogram. Subtraction represents the vector from the head of the vector being subtracted back to the tail of the vector in the first slot. See what else I need to tell you? See what's in what section, what's in the other. I know what I need to tell you. I showed you the 0 vector. A unit vector is a vector whose magnitude is 1. So our two standard basis vectors, I and j, have a magnitude of 1. But here's another example of a vector whose magnitude is 1. Calculate the magnitude and convince you of that.
I mean, that's one.
The magnitude of that vector is found by squaring this number, squaring that number, adding them together, and taking the square root. So it's 1/2 squared plus the square root of 3/2 squared. 1/4 plus 3/4, which is 4/4 or 1, and the square root of 1 is 1.
It's more funny.
Special needs, sir.
Is that why it's called? the-
In the XY plane, any point on a unit circle as the terminal point of a vector from the origin is a unit vector. Okay? And in 3 dimensions, any point on the ball, x squared plus y squared plus z squared is equal to 1, is a unit vector in 3 dimensions. The unit sphere. Speaking of spheres, let me see if you know how to find the center and radius of a sphere in 3 dimensions. Because you can find the center and radius of a circle in 2 dimensions, can't you? Okay, so here is the standard equation in 3 dimensions of a sphere. Here's a sphere centered at the origin with radius r. It's just x squared plus y squared plus z squared is r squared. If we shift things, h units to the right, or h units in the positive x direction. Oh, I don't want to go with h. Let's go a, b, and c. B units in the y direction and c units in the z direction. Then this is a sphere whose center is at A, B, C, and whose radius is r. If I took that and I multiplied it out, I will have an x squared plus a y squared plus a z squared with a coefficient of 1. But I'll also have some first degree terms in there and a constant term. So I want to see if you can find the center and the radius of, I've got one with pretty numbers, or otherwise you're just gonna get goofy numbers. Have any pretty ones? This one will be pretty. X squared plus y squared plus z squared. Minus 2x minus 4y plus 8z plus 17 is equal to 0. And you take an equation from its multiplied out form and put it back into its standard form. See if you remember how to do that by completing the square in each direction. Center and radius of that. See if there's anything else I need to talk about. Radius can be 2. I thought I could do, I can't find the center. Got a radius of 2. All right, so we're gonna move terms around. I'm gonna group the x's together. I'm gonna write that as x squared minus 2x, and then I'm gonna leave a gap right there. And I'm gonna do the same with the y's. I'm gonna have y squared minus 4y. I'm gonna put them in here. Leave a gap. We always add in between. And then we're gonna have z squared plus 8z. Leave a gap, and let's move that 17 to the other side. And we complete the square in 3 dimensions the same way we do in 2 dimensions. You add in those parentheses half the middle term squared. You add a number there, but I got to balance it out by adding that number here. I'm going to add a number here. So I got to add the same number here. And then I'm going to add a number here. Then I got to add it over here. There's some high-level math for you right there.
I wonder if you like gave this to like a super high, like somebody that's gonna go get like 6 doctorates in math or something, and they could give you an answer that's
Just in terms of clouds, triangles, and
Yeah.
squares. All right, so we said we're gonna put in here 1/2 the middle term squared. We don't really need to worry about the sign because we're gonna square it, and we're always adding in here. So half of 2 is 1, 1 squared is 1. Same deal here. Half of 4 is 2, 2 squared is 4. Out here, half of 8 is 4, 4 squared is 16. Now make the little box numbers match.
you don't actually really have to do that
Why not?
because you're adding.
Because you just do it in your head.
Because I'm adding them. I'm gonna add the same thing to both sides of the equation.
I know, but you don't have to match up the shapes and the numbers.
Well, that takes the fun out of it.
It's like whenever you were little, and you had a little thing you could shove the shapes through.
Before I got to teaching honors students, they had me teaching the elementary ed majors. They have 2 sequence math. And so you have to put clouds and smiley faces and things instead of variables. So now these factor as perfect squares. The square root of 1 is 1, and then I take the sign in here. So it factors as an x minus 1 all squared. If you multiplied that out, you should get that. Over here, I got another minus, square root of 4 is 2. So y minus 2 all squared. And then finally, z plus 4 all squared. And on the right-hand side, there's my 17 minus 17, so I just get a 4. So now it has that right form. The center is the A, B, and the C, so you have to think of this as z minus a -4. And so the center is 1, 2, -4, and the radius is the square root of that number over there. You done that before? Okay, so in 3 dimensions, something that is a line becomes a plane, something that's a circle becomes a sphere, something that's a parabola becomes a version of a cylinder, right? So you can have a cylinder that's shaped like a sine curve. In the XY plane, you got a sine curve, and then in the Z direction, it's got all those little hills and valleys. Right? And what we can do, and what you will do, is take these surfaces in 3 dimensions, and you will find vectors that are tangent to those surfaces. Well, when you find a tangent line, it just touches the surface in 1 point. In 3 dimensions, if you've got this lumpy old surface, your tangent vector will touch it at just 1 point, but it has a direction in the greatest rate of change at that position. So if you're on some point, I'll borrow your water bottle right here, your tangent vector would be pointing here. But then if I found a tangent vector there, it would point in the other direction so that you can describe the surface with various little arrows. So you'll be doing that like in your first week of Cal 3, drawing things in 3 dimensions and then using vectors, and you'll do calculus to vectors. So your vectors will have components that are functional. It'll have X, Y's, and Z's in them. We'll just deal with numbers. All right, so we see you again on Monday and Wednesday. Thursday's the study day. So on Monday, we're going to do the 2 vector operations that are associated with multiplication. One's called the dot product, one's called the cross product. Very easy to do. And then on Wednesday, we'll review for the final. I'll find an old final exam and I'll post it, and that way you can look at it.
Cal 3 honors.
I feel like most people who are taking Cal 2 really take the other higher.
I'm just gonna go to Chick-fil-A and back. Okay, yeah.
That's it? That's your lunch?
I'm gonna say, yeah.
You guys don't get sick of Chick-fil-A? Take a nap.
I haven't had it in like 4 days.
4 days.
Oh, my God.
That's an eternity.
It's really sad, actually. I love it.
They give him a death stare for missing class.
Yeah.